Welcome to our discussion of the combined gas law. In this video, we'll derive the combined gas law from the three individual gas laws, and then calculate changes in pressure, temperature, and volume using the combined gas law. So far, we've looked at three individual gas laws: Boyle's law, Charles's law, and Gay-Lussac's law. In Boyle's law, which is P1 V1 equals P2 V2, the relationship between our variables is indirect, meaning as pressure goes up, volume goes down, or as pressure goes down, volume goes up. In Charles's law, which is V1 over T1 equals V2 over T2, the relationship between our variables is direct. As temperature increases, volume increases. And finally, in Gay-Lussac's law, which is P1 over T1 equals P2 over T2, the relationship of our variables is also direct. As temperature increases, pressure increases, and vice versa. So notice in each one of these three laws, one of our variables isn't mentioned, which means it's being held constant. In Boyle's law, our temperature isn't mentioned, so our temperature must be held constant. In Charles's law, it's our pressure that's being held constant, and in Gay-Lussac's, it's our volume that's being held constant. But what if we actually want to look at all three variables, our pressure, volume, and temperature, and predict how each of those variables is going to change? For that, we need to combine these three gas laws into one, into our combined gas law. So when we steal the variables from these three different laws and combine them all into one big combination gas law, we get P1 times V1 over T1 equals P2 times V2 over T2. Now we have a formula that allows us to work with all three of our variables, our pressure, temperature, and volume, within the same equation. Do note, however, that for all of these gas laws that we've been working with so far, Boyle's, Charles, Gay-Lussac's, and combined, our amount of gas has remained constant. We haven't changed the number of moles of gas yet. So let's take a look at an example. If a gas has a volume of 39 liters at STP, what will its volume be at 4 atmospheres and 25 degrees Celsius? So for all of your gas law problems, what I recommend is organizing yourself first. Pull out all of your variables so that you can see what you're working with and what you have to solve for. So first, let's have our P1, T1, and V1, and then our P2, V2, and T2. And then let's fill in all of the numbers that we currently have been given in this equation. Do note that they gave us STP. Well, STP is standard temperature and pressure. And we know at STP, we have 1 atmosphere of pressure at 0 degrees Celsius. So STP actually gives us a temperature and a pressure. It's always going to give us 0 degrees Celsius for our temperature and 1 atmosphere for our pressure. So always keep that in mind whenever you see STP. So now that we've organized ourselves, we can fill in our values, being very careful to pay attention which of our variables should be on our initial pressure, temperature, or volume, and which value should be in our 2 section, our final pressure, volume, and temperature. So now we can very clearly see that we are solving for our final volume, our V2. So now all that remains to be done is to take all of our values and to plug them into our variables into our combined gas law and solve for our V2. So now when we plug in our values, we get 1 times 39 divided by 273. Remember, all of your temperatures need to be in Kelvin. And for your volume, it doesn't matter whether it's in liters or milliliters, but your volume units for your initial and your final, your V1 and your V2, have to be the same. So then on the other side, our P2 becomes 4, and we're solving for our V2 and we're dividing by 298. So now when we solve algebraically, we get a V2 equal to 10.64 liters. And we know that it's liters because our V1 was in liters, so our V2 units are going to match our V1. If they asked for our answer to be in milliliters, all we would have to do would be to convert from here. But since they didn't specify what units we needed, we can simply leave our answer in liters. Now let's take a look at one more example. If 100 milliliters of hydrogen at 0 degrees Celsius is heated to 20 degrees Celsius, what will the resulting volume be? So first we organize all of our variables. We have our P1, V1, T1, and then our P2, V2, T2. So once we fill in all of our values for our variables, we notice that our P1 and P2 are left blank. They didn't give us any information about the pressure. So what that tells us is that pressure is being held constant. So we're actually dealing with Charles's law. V1 over T1 equals V2 over T2. With our combined gas law, if one of our variables is being held constant, we can actually just remove that variable from the equation and solve from there. We no longer need to memorize our three individual gas laws. We can just use the combined gas law for whatever equations come our way and just omit the variables that are being held constant. In this case, pressure. So now we can fill in our values for our V1, T1, and V2, T2. So that I have 100 milliliters divided by 273 gives me V2 over 293. Then I just solve algebraically and I get V2 equal to 107.33 milliliters. And remember, it doesn't matter whether our volume is in milliliters or liters if they don't specify, as long as the units for your initial and final volume match. So for this V2, for our V2, our units must be milliliters because that was our units for our V1. And this concludes our lesson on the combined gas law. Bring any questions you have with you to class.